For benchmark 5.9, what we first need to do is fill in the table for each function, for f and for g. Now when you try to fill in these functions, these tables of each function, you don't always want to just start at the top at -3, because if you plug in -3 plus 1 is -2, and it makes it more complicated. What I would do is look for the easiest one. And usually the 0 or something close to 0 is easiest, meaning if I start with 0 here, what's 0 plus 1? 1. What's 4 to the first? 4. What's 4 times 16? 64. Okay, now you could also do -1, because what's -1 plus 1 is 0. 4 to the 0 is 1. 16 times 1 is 16. That's where I got my 16 times 1. Then, if you do a couple of them, let's say I just did those two problems, then you should notice there's a pattern. You can also notice right there, because the growth factor is a 4, so you're multiplying by 4. So you should see from 16 to this, you multiply by 4. So if I divided by 4 as I go up, and you can get these values. And then you could plug in -3 and check it, but you should also see that there's a pattern of multiplying by 4 and find the easiest number first. It's way quicker than finding every single number. Over here you should notice by this decay factor that it's dividing by 5 repeatedly. And again, you don't have to plug in -3. Let's plug in -1. If I plug in -1, -1 plus 2 is 1. So 1/5 to the first is 1/5. Alright? And if you have to keep going from there, you're like, let me try some numbers. Well, you could plug in 0, but if wait, I'm adding 2 here. So wouldn't that be, let's do a -2. Because watch, if I plug in -2 plus 2, that's 0. 1/5 to the 0 is 1. Now I got the middle 2, and if I'm dividing by 5, so that would be 125. As I go up, I'm multiplying by 5, so that would be 5, and I filled in my table. So again, find the easiest way to fill in your table. It needs to be filled in, but you don't have to compute every answer. Okay, from there, the second question is find the approximate solution. So the approximate solution is where these two graphs cross. And you've got to look at it carefully by looking at the values. And so what I do, you could graph it, by the way. If you graph these dots and you graph these dots, you will see the interval for which they cross. But I think there's an easier way, just looking at the table. Do you notice that G over here is bigger? And then we go to the next values. Do you see all of a sudden that F is bigger? So in order for all of a sudden for G to be bigger, and then F is all of a sudden bigger, that means there has to be a crossing between these two values, between -3 and -2. So that would be your answer. Now it could cross more than once, but as we watch, do you see how this is bigger now? And this is bigger now. So you're looking basically for where the functions trade off who's bigger. And then that interval between there is where they crossed. So that is kind of what we're looking for. It's kind of complicated. If you need to, you can graph these dots and graph these dots, and you'll see visually that somewhere between here is where they cross. Let's now talk about benchmark 5.10. In order to solve this, what you have to do is treat it like a normal solving. We want to get this piece right here by itself. So the first thing we always do in solving is get rid of the plus or minuses. So I'm going to -7. Then, to get this piece by itself again, I have to divide the 10 off, because it's multiplied on, so divide the 10 off. Our whole goal is to get to this point with the exponent on the left side. Then, you have to add in a new step. That new step is a logarithm. So here's where I got this. Now, what I do is I put the word log right here, and I switch the 3x plus 4 into 2. So when I put the log word right here, the 9 is your base. Make sure it's a lower number. Alright, and you see how I switched these two pieces? See, the 2 and the 3x plus 4 got switched. Now I have this log. Log 2 base 9 equals 3x plus 4. Now, this is a number. We don't know the value of it. It's saying 9 to what power is 2. 9 to the what power is 2. That's complicated. So we just leave it. It's something you can't really do without a calculator very easily. So we now just solve. So like all solve, we got to get x by itself. So I minus the 4 over. Then I have to get rid of this 3, so you divide it off, and your answer is just that ugliness right there. If you had a calculator, or you have a really good ability to approximate logs, you could get this answer and finish it off. But this is all I'm asking for, is something that looks like this. So again, you want to get it to this point change it to a log, and then keep solving. And just leave this log look there. Unless this can easily find a value, then you want to find the value of that and make it a whole number or a nice answer. All right, for this one, you do not need logs. The goal on this one over here is to get the bases the same. Now I have a base 5 here and a base 125 here. So my first look, my first thing is to look at the front numbers. I want to get those off. So what I can notice here is, if I divide both sides by 4, I now have a 5 out front and a 5 and so I have this. Okay. Now over here, what I did is I noticed 125 is 5 cubed. Because remember, our goal is to get the bases the same. So you have 5 and a 5, and I have a 5 out here, which is our goal too. We need this outer number to match that. Basically, all the lower numbers to be the same. That's what we're looking for, is the kind of the goal. So I have all my bases are 5s. So what I have to do, because 125 is 5 cubed, now I have 5 cubed to the 2x minus 9. When you take a power to a power, you multiply these. So when you multiply 3 times 2x and 3 times negative 9, it's called the distributive property. Over here, though, what you have to realize is this 5 in front is really 5 to the first. Then, if these are both base 5, what you have to remember with power properties is that you add powers. If the bases are the same, you add powers. Do you see 1 plus 6 is 7? Still got the minus 3x. Now the bases are the same. If the bases are the same, that would mean that for these two sides to be equal, the powers have to be the same. So we can kind of just ignore the bases. And then it's an easy solve. We just do the basic easy solve and we're done. So the goal is to get the bases the same. If you can't get the bases the same, this problem can't be done in this manner. But these problems are set up so that you can get the bases the same. So just watch out. One of them will usually have to have the same bases and you have to add. Where one of them, you're going to have a power to a power and you have to multiply. So keep track of that. That is a very common feature on this type of problem. Now, 511. We want to solve for t. Do you notice there are no numbers in this whole entire thing? It's a formula of some sort. And we want to get t right here all by itself. So that's r minus t. It's kind of hard to see. So to get t all by itself, we first got to just think about what operations could we do. Well, let's get rid of this p first. Okay, since it's divided by p, I can multiply both sides by p. All right, and I now have this in red because these p's cancel out. Okay, so I have this. I'm still trying to get this t by itself. So let's get rid of the k. The k is connected by multiply, so if I divide k off, okay, I now have apk, and over here I have e to the r minus t. Now if you look down here, how did I get to here? Do you notice I just switched this to this side and this to this side? There's a reason, because my next step, now that I have my exponent by itself, is I want to change it to a log. And these problems always have the need to change to a log. That's just the section we're in. So again, I like to get the exponent on the left. So how do I get the t out of the power? I have to put the word log right here. That's where this comes in. This is your base. And I switched r minus t and ap over k. Do you see how I switched r minus t is now over here, and ap over k is these two switched. And I have the word log. So now we're here as a log. And we got to keep getting t by itself. To get t by itself, I have to minus the r off. I like to put it in the front. So I put the r, negative r in front. I have a plus because we minused it over, so kind of like adding a negative. So I added a negative r. Now, where did ln come from? Well, anytime you have a log base e, you must write it as ln, natural log. So make sure anytime you have this, if there's an ln, and this benchmark will most likely have an ln. It could have a log of a different base. That is possible. But I tend to try to keep it with e's. But you could have it like, if that was a base 2, it would be log base 2. You're good. But it's log base e, so it's ln. Okay, next I got to get rid of this negative. So I divide both sides or multiply both sides by negative 1. Your call. But I divided both sides by negative 1. When I do that, I can actually simplify that because negative divided by negative is a positive, and a positive divided by negative is a negative. And that is our final answer. t is all by itself. So your goal again is look what you're solving for and start trying to get it by itself. And the key usually is you're trying to get an exponent like this and then change it to a log. So if you don't have a log, you're probably making a mistake because there probably needs to be a log at some point on this problem. Alrighty, let's look at 512 here. I want to find the inverse of this exponential function. So the inverse, the first step is always switching your y and your x. So see, that's x now, and that's y. That's our first step. And then our next step is to solve for y. And that's a little ugly. Now this one has a lot of numbers. The last benchmark did not. So for this one, I want to get y by itself. So we're first solving for that, we want to get rid of like plus or minuses first. So I'm going to add the 4 over. That cancels out. So I keep this on the right side, and I have x plus 4 over here. Then I want the exponent by itself, so I have to get rid of the 9. The 9 is multiplied on, so I divide both sides by 9. That cancels. And what you notice here, I move this one to the left, and this I put over here. That's kind of important. We did it on the last problem. You tend to want the exponent on the left because you're going to make it into a log. Because my goal here is to convert this into a log. To make it a log, because there's nothing in front or underneath, so we're going to put a log right here. And we're going to switch this and this. So again, put log, switch this and this. This is the base. So right here, log, we switch the two pieces. See, this is now on inside the log, and this is the other side. So we now have this right here, log base e, which we know log base e is going to become an ln. You should memorize that. Again, this one could end up without a e here. It could be like a 8, so that'd be log base 8. But this is log base e on this problem. So I want to now get y by itself. So let's add, since that's add 7, we're going to minus 7 over. That cancels. I now have here the negative 7 I put in front, plus the ln of all that, equals 5y. Now I have to divide the 5 off like usual, just getting y by itself, and the whole thing's over 5. So you have this ugly, ugly thing. You could graph this. It's ugly. But that's how you write it. There are ways to simplify it, but we're going to let this be. Y equals, this would be the inverse function of this. Whenever you start with an exponent, the inverse is always a log. Be aware of that. If your base is e, you're going to be ending with ln. If it's the base of a number, you just have log base, whatever that number is. So first step, switch x and y. Then we're solving for y.